Hello, hello, I am Mrs. Edwards, and today we are going to go over the remainder theorem. And the remainder theorem leads to the factor theorem. And so then, of course, we're going to factor some polynomial. To be able to introduce the factor theorem and the remainder theorem, I'm going to begin by just evaluating the function f at 3 and also dividing f of x by x minus 3. We're going to run those down on the same page here, side by side, so that you can observe some patterns, and then you will discover the remainder theorem. All right, let's go. As I said, we're going to start by evaluating this function f at 3. So we just grab that f function, replace all of the x's with 3, do some simplifying, and we get the answer 36. Okay, then right next to it here, let's take the function f of x and divide it by x minus 3. You could do that one of two ways. You could use long division, but since we are dividing by something of the form x minus k, we could synthetically divide, and that would be a shortcut. I'm going to go with the shortcut to divide, and the first thing I need to do is come up with the k value. The k value is always the opposite of this x minus 3, opposite there, so it's 3. Ready to set up the synthetic division. So putting that 3 there in the corner, putting the coefficients across the top. Notice we have 5, -4, and 3. And then I'm going to put in that little line that separates the remainder off to the side. Okay. Then if you did happen to watch how to synthetically divide from me in my last lesson, then you know to drop it down, multiply across, add diagonal, bring that answer down, repeat. All right, so let's go ahead and do that. I'm going to take the number 5 and drop it down, and then multiply across. 3 times 5 is 15. Add diagonal, 15 plus that -4 is 11. Drop that answer down. Repeat. 3 times 11, multiply across, 33. Add diagonal, plus 3 is 36. Drop that answer down. All right, so we have the answer. Let's go ahead and write that out there. Okay, so what do you notice? Looking at those side by side. What? All right, what just happened is the remainder theorem. So let me put that up here. Okay, so if we have a polynomial f of x, in this case we had 5x squared minus 4x plus 3. If you were to divide it by x minus k, so x minus 3, rather than doing all of this division, what you could do is substitute k into the function. So my k was 3. If I plug that in over there, then you're going to get the remainder without doing all of the division. Sad story, very sad story. There was a student of mine who they were given the problem something like x to the 36th power plus 9 divided by x plus 5. And they got started right away, and they never listened to the lesson because they were like, I know how to divide. I can do this. Next day, student walks into my classroom and is like, they're such a nice kid too. Oh my goodness. Edwards, are you kidding me? This is ridiculous. And they were so mad. And then they drop their book down, they take out this paper, and they start unfolding, 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 unfolding. They had actually long divided this problem to get the remainder. Oh, no, don't let that be you. If all you want to know is the remainder when you divide by something in the form x minus k, simply substitute the k into the function. No division necessary. And you're going to get the remainder as if you had done all of the division. Okay, so why in the world would we want to know what is the remainder if we're not going to divide? Well, let's go back to something you did a long time ago. What if you wanted to know if 7 was a factor of 2,468? Well, we don't have any divisibility rules for 7, so you would have to painstakingly divide. Oh my goodness, just takes forever. And then we finally get the remainder is 4. 7 doesn't even fit in. So we've had to do this entire division problem to find out that 7 is not a factor. Wouldn't it be great if we knew right away if 7 was a factor of 2,468 and we could just skip this process? Well, unfortunately, we don't have any divisibility rules for 7, but you did have a lot of divisibility rules. If a number ended in 0, you could divide it by 10. If a number ended in 0 or 5, you could divide it by 5. If it was an even number, you could divide it by 2. If the sum of the digits was divisible by 3, then you could divide it by 3. You had all kinds of divisibility rules that saved you a tremendous amount of time when you wanted to factor. Coming back to this problem here, is x minus 3 a factor of f of x? Well, you don't have to do the entire division problem to decide if x minus 3 is a factor. You would simply replace 3 in for x in the original function, because that's the k value, and if it ends up equaling 0, well, then it is a factor. And after it's a factor, well, then you might decide to actually do the division. So factor theorem, these are really closely related. So I care about a remainder because that leads to the factor theorem. F of x has a factor of x minus k if and only if, by conditional statement, the function evaluated at k equals 0. So we took x minus 3, then the k value is 3. If I substitute 3 into the function, I did not get 0. So, since f of 3 did not equal 0, x minus 3 is not a factor of 5x squared minus 4x plus 3. So let's do one more example. We have this function p of x, and we want to know, is x plus 1 a factor of p of x? Well, I don't need to divide to decide if x plus 1 is a factor. So I determine the k value, and so the k is -1. Then I simply substitute -1 into the function. So I go ahead and replace all my x's with -1, simplify, and we get 0. That means the remainder, if we were to divide p of x by x plus 1, the remainder is 0. Well, when the remainder is 0, then yes, x plus 1 is a factor. Okay, then just a little side note here that I can't help but mention. That also means that at -1, if -1 is a 0 of the function, if I were to graph 2x cubed plus 5x squared minus 3, that also happens to be an x-intercept. Okay, that's a little bit of a red herring there, but I had to say it. Okay, so back here to our main focus, we are able to decide if something in the form x minus k is a factor of a polynomial by identifying the k, you plug it in, and if it equals 0, then x plus 1 in this case is a factor. Now, since we now know that x plus 1 is a factor, how could we use that to completely factor this cubic? So if I said the number 3 is a factor of 111, to figure out what the other factor is, you would take 111 and divide it by 3. And then you would have 111 factored. So since we now know that x plus 1 is a factor of 2x cubed plus 5x squared minus 3, let's go ahead and actually do the division. So we can figure out what 2x cubed plus 5x squared minus 3 factors to be. To divide, we're going to set up the synthetic division. I have -1, which is that k value. I'm going to put the coefficients running across the top. Make sure, because we're missing an x term, that we have a placeholder there of 0 x's when we run those numbers across there. Okay, I have my dashed line to indicate the remainder. We already know that right there is going to be 0 because we found the remainder. Let's synthetically divide. So we're going to drop it down. So 2 comes down. Multiply across. -1 times 2 is -2. Add diagonal. Plus 5. So -2 plus 5 is 3. Bring that answer down. Multiply across. -1 times 3 is -3. Plus 0 is -3. Bring that answer down. Multiply across. -1 times -3 is 3. Plus -3. Add diagonal. Bring that answer down. No surprise that that was 0. Okay, so P of x is going to equal x plus 1 multiplied by, this is the result, so we divided a cubic by an x to the first, so we knew that it was an x to the second, so we have 2x to the second plus 3x minus 3. Okay, the answer that we got here, x plus 1 times this one equals our original. So we were able to use the fact that x plus 1 was a factor, so we divided and now we have it factored. I could go on to take a look at that quadratic right there and try to factor it, but it turns out that one does not factor. So we have completely factored this cubic right here.